Have you ever looked out at the ocean, seen a massive ship, and just wondered, how does something that big, basically a floating city, find its way across thousands of miles of open water with pinpoint accuracy? Well, today we're going to pull back the curtain on the incredible, unseen science that makes it all happen.
So take a look at this. This is the bridge. It's basically the brain, the nerve center of a modern ship. It's from here that a 200,000-ton behemoth gets its orders. But the question is, how do they do it? How do they get from point A to a point B that's halfway across the world? Let's dive in and find out.
You know, you'd think the journey starts when the engines fire up, right? But nope. For a ship, the journey of 1,000 miles begins way before it even leaves the dock. It all starts with a meticulous, detailed plan that's put together back on solid ground.
Okay, so this whole process isn't just a suggestion. It's a mandatory 4-stage cycle required by the International Maritime Organization. Think of it as a complete birth-to-birth game plan. First up is appraisal. This is the homework phase, right? You're gathering all the intel, weather forecasts, tide charts, potential hazards, you name it. Then comes the fun part, planning. This is where they actually chart the route from start to finish. After that, it's execution. Time to actually put the plan into action and sail. And finally, and this is crucial, there's monitoring. You're constantly checking and rechecking to make sure everything's going according to plan and the ship is staying safe.
And boy, have the tools for the job changed. We've gone from these beautiful, old-school paper charts, which were the standard for centuries, to something called ECDIS. And you gotta understand, ECDIS isn't just Google Maps for ships. It's a fully integrated, dynamic system that pulls in all sorts of data in real time. It's a total game changer.
All right, so the planning's done, the ship is underway. Now, once you're out on the open ocean, everything really boils down to two fundamental questions. Where are we right now, and where are we heading?
To answer those questions, you need a compass. But ships actually use two main types. You've got the magnetic compass, the old reliable. It's a mandatory backup because, hey, it doesn't need any power to work. The problem? You're on a giant floating hunk of steel, and all that metal can really mess with its reading. That's why the star player is the gyro compass. This thing is ridiculously accurate. It uses a gyroscope to point to true north, and it feeds that super precise data to the radar, the autopilot, the whole shebang. The only catch? It's got to have power.
And this is where things get a little weird, because there isn't just one north. There are actually three. First, you have true north. That's the geographic North Pole, the literal top of the Earth. Simple enough. Then there's magnetic north, which is where a magnet naturally wants to point, and that spot actually wanders around. And finally, you have compass north. That's what the compass on the ship actually says, which, as we just mentioned, is affected by the ship itself. So yeah, navigators have to juggle all three of these to know where they're really going.
So how on earth do they manage all that? Well, it's all about making corrections. It's a step-by-step process. They start with the true course, the one they plotted on the chart. Then they apply something called variation. That's the difference between true and magnetic north at their specific spot on the globe. Okay, so now they have the magnetic course, but they're not done. Next, they apply deviation to correct for the ship's own magnetic field. And what you're left with is the compass course. That's the actual heading the person at the helm needs to steer. It's some seriously important math.
Now, of course, a lot of this complex math is made way easier by modern technology. We're talking about Global Navigation Satellite Systems, or GNSS. You know them as GPS, but there's also GLONASS and Galileo. These satellites are constantly beaming down incredibly precise data about the ship's position, its speed, the time, everything. This fire hose of information is the absolute backbone of modern navigation. It feeds right into the ECDS and radar systems, giving the crew a perfect real-time picture of exactly where they are.
Okay, so think about it. You've got thousands of these massive ships all over the world's oceans at any given moment. It sounds like a recipe for absolute chaos, right? But it's not. The high seas are actually incredibly orderly, and that's because there's basically a highway code for the ocean that every single sailor has to follow.
Just like our roads have traffic signs, the ocean does too. They're called aids to navigation, or ATON for short. You're probably familiar with the physical ones, lighthouses, and of course, buoys, like these. But now, there are also virtual ones, basically digital markers that pop up on the electronic charts to show you where a safe channel is, or maybe warn you about an underwater pipeline.
And the really cool part is that these aids all speak a universal language. It's a standardized system so a sailor from anywhere in the world can understand it. You've got lateral markers, which are kind of like the white lines on a road. They mark the left and right sides of a channel. Then there are cardinal markers,
which tell you where the safe water is in relation to a hazard. It's like a sign saying, hey, pass me on the north side to be safe. And then you have special markers, which just point out, well, special things, like a good spot to anchor. But the absolute Bible, the most important rule book of them all, is something called COLREGs. That stands for the International Regulations for Preventing Collisions at Sea. This is the law out there. It covers everything. Who has the right of way, what to do in a narrow channel, how to act when visibility is bad. It has one single overarching goal: to make sure ships don't run into each other.
So, you can have the best plan in the world, the best charts, and know all the rules, but that's still only half the battle. Because once you're out there, you're constantly wrestling with the immense, invisible forces of nature.
A ship on the water is never truly still. It's always moving, and it moves in 6 distinct ways. You've got 3 linear motions, surging forward and back, swaying from side to side, and heaving up and down. And then you have 3 rotational motions, rolling side to side, pitching front to back, and yawing, which is when the nose turns left or right. The crew has to manage all of this, all at once, just to keep the ship pointed in the right direction. And while they're doing that, they're also constantly battling all these external forces. Yeah, you've got the big ones, wind and currents and tides, obviously. But there's also some really subtle, weird stuff. There's something called the bank effect, where the hydrodynamics can literally suck a ship toward the bank of a river. Or the squat effect, where a ship actually sinks lower in the water when it's moving fast in a shallow channel. It's wild.
So with all this going on, the absolute #1 priority is stability. It all comes down to a concept called metacentric height, which is basically the relationship between the ship's center of gravity and its center of buoyancy. To put it simply, if a ship is stable and a big wave pushes it over, it will naturally want to roll back upright. If it's unstable, well, you're looking at a potential catastrophe.
All right, let's talk about the grand finale, the final approach. This is where everything we've talked about comes together in a high-stakes performance. Believe it or not, those last few miles into a busy port are often the most challenging part of the entire voyage, demanding absolute, nerve-wracking precision. Getting into port safely isn't a one-person job. It's all about this triangle of constant communication. You have the ship's master, the captain of the vessel. You have the local port pilot, an expert who comes aboard to guide them in. And you have Vessel Traffic Services, or VTS, which is exactly what it sounds like, air traffic control but for ships. These 3 have to be in perfect sync for it to work.
And the maneuvers themselves are just incredible. Pilotage is when that local expert comes aboard and uses their knowledge to navigate the tricky local waters. Berthing, well, that's the delicate art of parallel parking a literal skyscraper, usually with the help of a few powerful tugboats pushing and pulling. And then there's anchoring, which isn't just dropping a chunk of metal. It's a calculated move to secure the vessel in exactly the right spot so it holds fast against the wind and the current.
So, what's the big takeaway here? Navigating one of these massive vessels, from the initial planning to the final parking, is this non-stop cycle. It's a constant dance of calculation, keen observation, and quick adaptation. It's a beautiful blend of ancient maritime principles, some really complex math, and cutting-edge technology, all orchestrated by a crew that has to be at the top of their game.
It really is this unseen science that keeps our entire global economy afloat. So the next time you're at the coast and you see one of those giants on the horizon, maybe you'll think about it a little differently. You'll imagine that invisible dance of forces, calculations, and skill happening on the bridge. It makes you wonder, right? Now that you know what's happening out there, what unseen forces and calculations will you imagine at play?